My name is Mike Mankus. I work for the Spectrum Testing and Engineering Analysis team in the FAA. I am the manager of that team. I manage a team of 8 engineers. We are responsible for doing all the engineering analysis that goes into any type of new proposals for how to use the radio spectrum. So we have a really clear and concise mission, making sure that there is safe and efficient air travel. That's the bottom line, right? But the way we do that for the Spectrum Engineering Group is making sure we're properly securing, managing, and protecting all the frequencies used for aviation. We break everything into 3 sections in aviation. We break it into communications, navigation, and surveillance. And we do have 30,000 frequencies. And the challenge with those frequencies is that they're not all in a single block. It's not like 100 megahertz to 2000 megahertz covers the aviation frequencies. We're all over the place. So we have communication systems that are generally kind of in what we call VHF communications. So they're like 100 megahertz to maybe 400 megahertz. We've got navigation systems that are all over the place. We've got them just next to the FM radio stations that you listen to in your car. We've got them a little higher up at like the 3 gigahertz range. And then we've got surveillance systems that are all over the place. So we've got multiple different types of radars. But all these systems are designed for us to know where an aircraft is, know where it's heading, be in constant communication with those pilots, so that if they've got a problem, they can relay it to us. If we've got a problem, we can relay it to them. Most people, when you drive by the airport, you'll see at some location near an airport, large building with a giant spinning dish. Those are our radar systems. We have multiple radars in the FAA, but they're usually a system called ASR, or Airport Surveillance Radar. So that's why they're typically installed around the airport, right? And those operate from 2.7 gigahertz to 2.9 gigahertz, sometimes as high as 3 gigahertz. You know, all these different components come together to build what we call the National Airspace System. And it's really a distributed system throughout the entire country. So you can imagine we have ground transmitters and receivers for all these different things, right? So there's a ground-based communication network all throughout the country of ground transmitters and receivers. And then our passive radar systems, for example, again, are all scattered throughout the ground. Aircrafts have a lot of different ways to tell their altitude above ground level. They've got GPS, which is using a satellite-based system to tell them their height. Now, generally, GPS is going to give an aircraft their height above the mean sea level, not their height above the specific ground level. Then they've got typically a barometric altimeter, which is using atmosphere pressure to tell them how high they are. But again, that's generally telling them how high they are above mean sea level. There's really only one system on an aircraft that can tell them how high they are above the terrain itself, and that's the radar altimeter. So those systems operate from 4,200 megahertz to 4,400 megahertz. There's a dozen systems that operate on the back end of the altimeter. So those are things like reverse thrusters. That's an example. So on certain aircraft, when they're going to land, the runways aren't long enough for these aircraft based on how big and heavy they are. And the aircraft has to fire reverse thrusters to help slow them down when they land. And what we found was that that really needs to happen automatically, and rather than via like pilot interaction. So the altimeter is a system where when the plane reaches a low enough altitude, those reverse thrusters automatically kick in. So, you know, that's one example. There's a dozen other systems that sit on the back of the altimeter. But, you know, when some of these systems become so crucial to the functioning of the aircraft, that's why it becomes really important then that we protect those frequencies, and becomes really important that we make sure there's no interference or things that can cause them to go wrong. Yeah, so radio frequency interference absolutely does happen, and it can happen for a lot of different reasons. I will say the first step for prevention for us is trying to adequately do our protection activities correctly. So that's making sure we're assigning our frequencies right and that we're doing accurate modeling and simulation. but interference is going to happen anyway. So it can happen for a lot of different reasons. If you heard about 5G in the news over the past 2 or 3 years, a lot of that news cycle was around 5G frequencies in the US that were being turned on from 3.7 to 3.98 gigahertz. And if you remember, I said the altimeter is 4.2 to 4.4 gigahertz. So they're not right next to each other, but they're pretty close to each other. And 5G transmitters were going to go all over the country, including installed right at your airport. So the potential was there for these really sensitive radar altimeter systems to be able to basically be interfered with from these 5G systems at the most critical time as the aircraft is landing at the airport, when all these safety systems that are built on the altimeter kick in. We've also will experience interference that just happens naturally occurring. So that could be the weather changing the way the signal propagates. We tested some really kind of things that would maybe surprise you. Like we tested pacemakers. We tested anything electronic, right? That could be on an aircraft roughly 10 to 15 times a year throughout somewhere in the country. There'll be someone who's intentionally trying to impact aviation. These are kind of on an escalating scale of severity. So all these different things kind of fall into that bucket of radio frequency interference. And we'll say in the FAA, we get roughly 200 documented reported cases of interference per month. And that's throughout the country. What we have seen is that the challenges thus far the biggest opportunity we've seen is towards collaboration that hasn't happened at the level it's been happening recently. So the most recent example of that to give would be the 5G and radar altimeter crisis. The FAA is not a regulator for 5G companies. Their regulator is the FCC. But when this crisis kind of came to a head, all of a sudden the FAA was meeting daily with the top 5G companies in this country, working on technical solutions for how to make these systems coexist. And that's exactly the type of collaboration that needs to be happening all the time, rather than having a regulation change come in from the FCC or the federal government, and then us having these industries find a way to coexist after the fact. I think the real opportunity here is for these industries to come together ahead of time, and then propose these changes for how to relocate the spectrum or reuse the spectrum after we've done all the engineering. We work with a lot of different people. So our spectrum group is even pretty diverse if I just look in the spectrum group. So we've got a division in spectrum where I like to call them engineering politicians. They're actually going and representing the US in international functions, and they really are ambassadors for the US, but also have to have a strong RF engineering background. We've also got folks in the spectrum group who are attorneys. We have folks that are economics majors, because all those different factors come into play when we're talking about repurposing of spectrum. We're looking for people who have a strong sense of like how to interpret regulations. So they kind of almost have like a legal mindset as well. They've got usually a strong analytical mindset in terms of how to view requirements of a system versus resources and constraints and find a solution. The core thing that we're always looking for is someone with a strong RF background. But it's very easy when you're doing spectrum engineering to get very down in the weeds of the dBs and the field strengths and all these different parameters that are terms of art, but also very specific. Being able to extract those to a higher level and communicate them to things, that's a really key skill set in the FAA that is hard to find in addition to the RF knowledge.